Right. I might be a bit off topic from all the verification people, but I'm going to assume that you all care about having fast code. Previously, the deal would have been, if you want your code to get faster, you can basically just write your software and the hardware guys will deal with it for you, right? Like the hardware keeps getting better and better. And the contract that we had before was that if you wrote a bit of software and it ran on yesterday's hardware, then it should do exactly the same thing and it should run absolutely fine on tomorrow's hardware. Except that this is now starting to break down because hardware is now becoming more and more specialized as Moore's law is dying. Is Moore's law dead? I feel like this graph was probably in a slide during my undergraduate, but let's assume that Moore's law is dying. So we're now making hardware more specialized, and every new bit of hardware comes with its own new domain-specific language. So if you write your new software in this domain-specific language, you get these amazing performance gains, but what happens to the code that you wrote yesterday? And to make this a little bit more concrete, let's talk about machine learning. Your machine learning workloads are dominated by tensor code. The key to making this efficient is to use highly parallelized dense algebra. If you write your machine learning code in a new DSL like TACO, which is a specific subset of C, it basically it's Einsum notation, looks like matrix multiplication, your code will be really fast. But if you wrote your code yesterday and you wrote it in C, what are you going to do? You're going to have to pay some developers to rewrite it, basically, or you're going to have to suffer through having slow code. Unless you could use C to TACO, which is the work that I'm going to talk about. So this is a collaboration with Mike O'Boyle at the University of Edinburgh, and it's led by Jose, who is one of the PhD students. So purple box is C code. The little green box at the top is the equivalent TACO expression. Doesn't that look so much better? And if you write your code in the TACO expression, you can use the TACO compilation infrastructure, which means you get highly optimized C code for CPUs or for GPUs. The trick is, how do you get from the purple box to the green box? Existing approaches. You could use an API matching, sort of rewriting syntactic approach. But that's pretty brittle. They are out there, but they are somewhat, they work for certain benchmarks, but they're not a very general approach. It's very easy to overfit when you're building these things. Or you could use neural machine translation, maybe just ask ChatGPT, except you need quite a lot of data for this to work. If you are writing in the new DSL for the latest hardware, you probably don't have that data. ChatGPT probably hasn't seen that data either. Let's use program synthesis. I'm somewhat motivated to do this because I like program synthesis. That's my background. So I'm going to dip into some formal synthesis definitions so that everyone is roughly on the same page for 5 minutes. So, formal program synthesis tries to solve the formula, does there exist a program P such that for all possible inputs X, some specification, sigma, holds true for all of the possible values of X? The specification is a quantifier-free formula in a background theory, so that could be linear integer arithmetic. And it's worth noting that you can write input-output examples, so like the program should return 10 when I give it 7 as a quantifier-free formula. So this covers programming by example. As an example of formal program synthesis, this is one such spec, which I stole off some slides from the people who write CVC5, one of the best syntax-guided synthesis solvers. I don't know if you can read what's on the slide here, but the spec is that the program must return a number that is greater than or equal to both of the inputs and must be equal to one of the inputs. So I can write this as a logical formula, and I can give you the solution. This specifies a function that finds the maximum of both the inputs. Fine. A paradigm that is relevant to this is that you often want to define a search space for possible programs, and you will do that with a syntactic template or a context-free grammar like the one shown underneath. And when you want to solve these problems, you will use something called oracle-guided inductive synthesis, where you'll have a learner which will search this program space and will guess candidates, and you will have an oracle who will say if the candidate is correct or not and will guide the search in some way. So a very classical version of this, the original version of this, is counterexample guided inductive synthesis. So the synthesis proposes a candidate, and the oracle is a verifier, which will give a counterexample if the candidate is incorrect. And then the synthesizer will try and find a candidate that works for the counterexamples it's seen so far. And then the results you get are guaranteed correct unless it can't find a solution. So now you know everything about formal synthesis. How are we going to apply this to lifting C to TACO? Okay, so these are the things you need to apply formal synthesis. Now we're going to find out what we have in the C to TACO problem that we can put into all of these holes. So first of all, we need a spec. This is my spec. Does there exist a program in TACO that does the same thing as my program in C for all possible inputs? Now, this is a very nice spec to have. This would actually be quite hard to check. So what I'm actually going to do is I'm going to give you a bunch of input-output examples over this program for now and say that the behavior has to be the same, but we'll come back to that later. So now I have a spec, and I also kind of have an oracle, right? Because if I've got input-output examples, I can just execute both programs. I can compile both programs and execute them and check that the behavior is the same. This is not very satisfying if you're a formal person, but let's just say it'll do for now. We can do a lot of testing on these to show they're equivalent. Now what I need is a learner to complete this loop. So I need something that searches a program space and guesses candidates. Fortunately, DSLs always come with a nice, well-defined grammar. So that's my program space. This is the grammar for TACO. That was easy to get. What I need to do now is I need to search this space of programs. And we decided to take a classical search method from the formal synthesis literature. We are going to do bottom-up enumeration. So let's suppose this grammar at the top is the TACO grammar, because this simple grammar would fit and the TACO one wouldn't. We're going to start off with all the programs of length 1. We're going to put them into our pool of programs we've got so far. And then when we want to get the programs of length 2, we're going to use the production rules to get the programs of length 2 that we can build using the programs of length 1. There's those ones as well, and also these ones, and there's quite a lot. And you can sort of start to see that I've got a bit of a problem as I increase the length of my programs, right? So I couldn't fit programs of length 3 on my slide. And I've got a bit of a problem that I've got an exponential search space. So another key part of building a learner for formal synthesis is that you need to think about how to deal with the fact your search space is massive. So we did a couple of tricks. The first one is that instead of enumerating complete programs, we enumerated templates of programs. Essentially, wherever there was an input argument, like an input to the function, we replaced it with a big question mark. And then we extended the oracle that checks whether the program is correct to check whether there was an assignment to those question marks that made the program correct. So this is a trick that we stole from the literature. This is essentially a trick that we stole from a paper called CGIS-T that we wrote a number of years ago. So this somewhat speeds up the search. Question?
It's still an exponential search space?
Yes. Still exponential, but better. Everything is undecidable. I'm living in a world where we can't solve any of the problems, so we're just doing our best. And the other thing we do to sort of reduce this somewhat is to prune by observational equivalence. So if we have a small set of inputs, if multiple candidate programs behave the same on all of those inputs, we discard all but one of those. This was not very colorblind friendly, sorry. If you can see the highlights, all the yellow ones are the same and the green ones are the same, so we could discard one of each. And this is, you can think of this as another oracle, by the way, this observational equivalence oracle in our oracle-guided inductive synthesis paradigm. So we've got all the bits, I think, to build a formal synthesis algorithm. And here it is. Here is our full workflow. So you can use C2TACO, you can give it a big bit of code, P, and then we have a program classifier, which is trained to identify fragments that it thinks it can lift. It picks out a fragment, it gives it to our C2TACO synthesizer. Our C2TACO synthesizer does Oracle-guided inductive synthesis, as described, with one box that I haven't told you about. We have some other heuristics which are based on doing a static analysis of the code and filtering out things that we think are most likely and trying those programs first. Essentially, we look at the operations that appear in the source code to bias our search. C2TACO will generate you this little fragment of code in TACO, and then we insert it back into your original code P. It works remarkably well. So the top graph, the black bars are C2TACO, and the vertical axis is the percentage of benchmarks taken from the literature that we could lift. C2TACO has the highest proportion of benchmarks that it can lift. For comparison, the green line is a very simple enumerative search that we implemented, so that's also us. And the interesting ones are the grey line is a neural machine translation that we trained with synthetic data, because that was the only way we had enough data. And the purple boxes are ChatGPT, which was really bad at it. You can also see at the bottom the average synthesis time. So ChatGPT is the purple line right down there at the bottom, and the neural machine translation is the green. Those are reliably fast, but bad at giving you correct answers. TF Coder is another tool from the literature. It works pretty well for a few benchmarks and then gives up and gets stuck. And the dotted line is C2TACO, which is reasonably quick most of the time and reliably solves the benchmarks. And you get massive performance gains. If you run this on a GPU, you can run some of our benchmarks 100 times faster. On average, it's 24 times faster on your GPU. How much time do I have left? Okay. Oh, brilliant. Okay. We also did this for MLIR, which is a set of dialects for LLVM. We implemented a similar synthesis procedure where we lifted between dialects from low-level dialects in MLIR to high-level dialects. And this is also a collaboration with Mike, and Alex is the PhD student that led this. This is just showing you some of the dialects, but the interesting thing is the speed-ups on the bottom right in the graph. So if you lift from the lowest level C program up to HLO, and you do that, the HLO dialect, and you do that using our automatic synthesis procedure, you can have a speed-up of 800x. Obviously, you could have this speed up if you did that lifting by hand, but you can have the speed up without having to pay the developer to do it for you. And the nice thing about MLIR synth I want to highlight is we get the grammar for free here, because whenever anyone creates a dialect in MLIR, they write a grammar file in the required syntax for a grammar file for MLIR, and we can just parse it in and use it automatically. It's fantastic. It takes away one of the biggest challenges of using a synthesis tool. Other than that, it's very similar to the C2TACO synthesis with some slightly different heuristics. And we got slightly better at checking the specification for MLIR synth. So instead of just doing testing, we do testing to guide the synthesis, and then after the synthesis produces a result, we use CBMC, we use bounded model checking to check equivalence. And we can provide various levels of equivalence guarantees for different benchmarks. So for some of them, we can prove that they are floating point equivalent. For some of them, we cannot because they are not. But if you live in compiler land, apparently that's okay. I found this very disturbing information to be told, but apparently it's fine. And compiler optimizations can change the order of floating point operations. For some of them, we can prove floating point equivalence with a small delta, and for some of them, we can only prove that they're equivalent using integers. But that is still better than nothing. And we get, synthesis time is pretty tractable, and we get some good speed-ups. So taking really simple synthesis techniques from the formal synthesis world has given us really big performance speed-ups and been surprisingly effective. There are two big limitations. The first is that we had to handwrite some heuristics to make this work. The heuristics we took from the program analysis involved us looking at the programs and deciding what we thought would be interesting and possibly useful as heuristics. And the second limitation is the correctness guarantees. And addressing the first one of the things we're currently working on is how to learn these heuristics automatically. So we've been looking at learning these using reinforcement learning and LLMs in the world of syntax-guided synthesis. And now we need to move this to the real-world problems, like the real code, rather than the pure syntax-guided synthesis benchmarks. And the other thing we are currently looking at is how can we provide stronger guarantees of correctness. And if anyone has ideas on that, I would love to hear them. And yeah, so there's still a lot of work to do. Also, currently recruiting for PhD students, and I have some much sought after international funding. So if you know anyone good who would like to do a PhD in this, please email me.
So we have time for a couple questions. Okay.
So you on the performance graphs, you compared your approach with other synthesis approach. Have you compared it with perhaps a decompiler? I mean that would completely.
Sorry, have I compared it with what?
With a decompiler from C to Taco. So if I were to write a decompiler. Decompiler.
I've got my original code is in C. So the question is, can I...
Inverse direction. That's what he's asking.
Can I go from Taco to C? So
no, C to Taco. So
yeah.
It's a decompiler which will take a lower level language like C and convert it into Taco, right?
Well, that's what. So we are lifting from we're going from a lower level language C into Taco.
Yeah.
You can't. So you could write your own compiler that did that, but it would be very brittle because you would have to write a lot of rules to do it. And one of the pieces of work that we compared to is effectively doing that. Is doing that conversion using standard rewriting rules, and it gets much less coverage across the benchmarks. Does that answer the question?
Yeah, I was wondering. On the performance side, I think decompiler would fairly outperform the synthesis because it's a deterministic function from one language to the other. There is hardly any hit and trial.
So the time that it would take for a compiler, if you had written a compiler from C to Taco, a compiler would probably be faster to run than the synthesis. I think the performance you would get on the end code is probably going to be pretty similar because the performance gains come from lifting to the target language.
Yeah.
But you could write your own compiler from C to Taco, but it would be brittle and you would have to write it. And then what about when the next DSL comes along?
The one part that was very surprising, and I'm still trying to process, was the use of this bottom-up enumeration.
Yeah.
So by saying it's simple, and the rest of it must be really good for that to work so well, do you think there's other things you could stuff in there and get yet further gains, or does it sort of not matter? The rest of it controls what the...
There definitely are things we could stuff in there instead of bottom-up enumeration. So bottom-up enumeration is the simplest synthesis algorithm you can build. So it seemed like a good starting point. I was surprised it worked. The key to making it work is the good heuristics and the fact that grammar is quite small. But there obviously are benchmarks where we failed due to scalability issues. And if we started taking more sophisticated synthesis algorithms from the literature, I think we could address some of those.
Were these heuristics in the implementation of the bottom-up search? You mentioned heuristics a couple of times, and I didn't quite get it.
Let me go back to, okay. So the green is no heuristics, the black is with heuristics. And these heuristics are things like, if there is a lot of multiplication operations in the original source code, we assume it's likely there's a multiplication in the Taco. But yes, I guess the answer is yes, there would be better things than bottom-up search. One of the, because bottom-up search is not what the standard synthesizers are doing that are winning syntax-guided synthesis competitions now. Does that answer that?
It does. It's still surprising that you did so well with that.
It's surprising to me as well, I have to be honest. I did not expect naive synthesis to be this useful.
Okay, I think we've got time for one more question, if anyone has any. If not, we can thank Elizabeth for her wonderful talk. Thank you.